What's that? So I shouldn't yawn, is that what you're saying? I'm going to just wait till the time windows. Yeah. Okay, it's time. So, I mean, I enjoyed meeting with those of you that I've met with over the last couple of days on the face-to-face check-ins, so thank you for that. Lots of people making a lot of progress on projects. I think it's going to be, oops, it's not on? Thank you. Now it's on? Okay, there you go. A lot of people making a lot of good progress on projects. I think it's going to be a really fun final sort of presentations. We're going to post the details of, it's already on the website, the details of what we expect from the project presentations, but a few of you asked during the face-to-face. One thing that I'm really looking for, and I think that you should all look for in the other people's presentations, is, sure, tell us why why you picked the problem, something about the problem, what you accomplished. But I am most interested in understanding what surprised you, like what you thought was going to work, but really didn't work, or what you weren't sure if it was going to work that worked beyond your, wildest imagination. Those are the things that I think we can all learn from. The places where we deviated from, the understanding that we've given you so far in the class. So the times are inevitably super short because there's many of you and not a lot of time, but we'll make it all work. Okay, so partly because I shuffled the lecture order a little bit, partly because a lot of people in your projects actually are thinking about some form of stochasticity or noise, or thinking about robustness in some sense. So I thought it'd be good to make sure we covered that this week, in case it helps anybody. I know it's already late in the term. And in general, I'm trying to introduce a few of the extensions, the big extensions to the modeling frameworks we've given you so far this semester. There's a lot to know about stochastic systems, and we're going to do a week of it. But I think I can give you some of the core ideas in a way that's hopefully useful and can lead you to further study if you're interested. So model systems with stochasticity. It's actually interesting. I think a lot more people these days know the language of probability, right? I think probability is the language of machine learning, and that's gotten so popular that I think a lot more of you are comfortable with those tools. But at the same time, I think it's easy to throw around the tools from probability, take log probabilities or take max entropy kind of objectives, and not realize how beautifully probability and dynamical systems play together. Okay? And the goal of this class really is to make you love dynamics. So today, I want to do a treatment where we talk about what happens when you mix probabilistic reasoning, and probabilistic models with the types of dynamics we've been talking about already in class. So the equations actually are pretty easy. I mean, that's one of the great things about probability. Everything's pretty easy. I didn't require probability as a prerequisite, right? So if you know probability, then these are easy. I think even if you don't know all the mechanics of probability, I think a lot of the intuition is going to be pretty graphical, I think, today. Okay, and the change to our equations is actually fairly small. So far in class, we've been using continuous time systems, roughly of that form, and discrete time difference equations of this form. And today, we're going to start using probability. But the first change we can make, and actually the primary way I like to think about the stochastic processes, is still with equations that look basically like our differential equations. So what I'm going to do is we're going to keep this sort of differential equation sort of language, but we're going to add in an extra input. We can do it in discrete or continuous time, where this W is the canonical name for this is the some random variable, and it's the output of some random process. So I'm not going to immediately, although it's easy to start just writing things in terms of conditional probabilities, I want to maintain this beautiful dynamical system structure that we have, this structure in the equation F, and first think about concentrating all of the randomness that comes into the system just on a new input, W. Okay, so W can model a lot of things. When I write it this way. So it can certainly model disturbances. If you're a UAV flying in the wind, and the wind is a random process, you can talk about the contributions of the wind to your dynamics and bring them in certainly this way. But this language is also useful if you have, for instance, model uncertainty. Or even modeling errors, or even model changes. So if your dynamics is changing over time, you don't know exactly how it's changing, it's a reasonable thing to say, I'm going to model the uncertainty or the changes in my mass for something as an additional random input that affects my dynamics. And there's various ways to talk about any particular change in your model that you want to capture that way. And then, there's ways that you could formulate that. But this is a very general thing to say, right? I'm saying I'm going to take a random variable and stick it through a nonlinear function, an arbitrary nonlinear function potentially. So I can take even very simple distributions, Gaussians or uniform distributions to generate these processes, and then shape them arbitrarily with my function f. But we're not yet modeling with this. You can certainly, with an extra set of equations, you can cover these extra things. But let me just distinguish this, that what I'm not doing in that set of equations is measurement noise, for instance. That's sort of a different thing. That would be adding, something similar to my output, but we're not even talking about output here. So this stuff, we would generally call this process noise. And there's, sensor noise is sort of a different, super interesting thing. We can get into that. But this leads you into topics of, for instance, state estimation and the like. And I'm going to just ignore that for today. I'm going to focus on, even if we have perfect state measurements, we're able to perceive X, we want to think about the role of just the world being random. Okay. Of course, these go together. I'm just trying to focus a little bit. Okay, now I want to connect, I want this to be very, like I said, very intuitive and very graphical. So let me just start by the simplest sort of example, and I'll do it sort of with a physical model instead of the typical simple equations. Okay, so let's think of a particle in a bowl, let me say, in a potential well, but I'll just call it a bowl here. Okay. So this is the picture I'd like you to have in your head, is that I've got some state x, and I've got some potential function, call it u of x. And you could think about a particle or like a marble or something that's rolling around in this potential function, and in general it wants to go downhill. Okay, this is something you already know, but it's a particular choice of, I'll say that the dynamics of my thing are always governed by going downhill on some potential function. The simple one, of course, is if I have a quadratic potential, then that just leads to the linear dynamics. Okay, so you'd expect a linear dynamical system to, sorry, I missed my half here, right? But you'd expect this linear dynamical system to be sort of have a stable fixed point at the origin, assuming that alpha is between, I guess it's 0 and 2 in this case. It should be 0 and 1. Why did I say that? Ah, my discrete time system is 0 and 2. Okay. So there's one thing about this. Okay, let me just say of these possible choices, I'll spend most of the time today talking about the discrete time system, and that's because it just takes a little bit more work to be careful about having continuous time random processes. Of course, it's certainly possible, but these are sort of easy, and you just pull every time you get a new n, you just pull from the random number generator, for instance. It's very easy to think about. Okay, so I'm going to do one extra step here and say that xn plus 1 is going to be, I'm going to make a discrete time approximation here, xn minus alpha xn. So that's like having my time step of dt is of size 1. And then I'm going to add additive random noise. And we can think about, for instance, saying that Wn is just pulled from a Gaussian distribution with mean 0. So this would be a normal or Gaussian distribution. This is the mean. This is sigma is the standard deviation. That'll be a common choice for today. It's not an exclusive choice. Okay, but so by virtue of having chosen my time step to be h equals, or my dt to be 1, I've actually changed the stability properties of this a little bit. Let's think about just the deterministic version of this. I have xn. In fact, I can even just integrate it. Xn is 1 minus alpha to the n times x0. So you can see from that easily that this is exponentially stable when alpha is between 0 and 2. Okay, so here's my first question for you guys. Now I'm going to put Wn back in. I'm going to let Wn be drawn every time step. I'm going to draw it from a Gaussian distribution. For what parameters of alpha is the system still stable? Is there still a fixed point at 0? You have to think about it for a second. The definition of a fixed point is that the difference, that if I put x in at 0 here, I should get x equals a 0 here on the way out. But if I'm adding some random number to it every time, then even if I start at the origin, I won't stay at the origin. So even though I had a fixed point for the deterministic system, the notion of a fixed point is gone. Okay? If you ask me about stability, okay, is there a limiting behavior as x goes to infinity? What's the limit of x? Again, that's kind of the wrong question, right? X now is a random variable, right? So every time I simulate the system, I'm going to get a different x for each n, right? So converging in the way we've talked about stability and in deterministic systems is no longer the right language for this. Okay, what we're going to see is that for some of these systems, the distributions of x, the statistics of x, will converge. And we have to lift our discussion from what happens to x to what happens to the probability distributions governing x. Okay, and that's the number one message, which I'll tell you a few times throughout the lecture, and we're going to give you some intuition about how that works in a lot of the systems we care about. Okay, so I'm going to stay on this middle board here. Let's dig into that a little bit. Let me start with an example, a numerical example, just to make sure we're intuitive here. I think that using this notion of a potential function is at least for our first few examples, it's just a little bit more. Most of the same equations I've already given you, I could give you a potential function interpretation of it. I feel like when we start talking about what happens to the distribution, it's sort of easy to think about in the potential function. So let me use the potential function again here. So for instance, the cubic polynomials that we've used before, but now with some noise, you could think of that as coming from a quartic potential function. Let me use this one. So this is a function that looks like this. This is positive 1, negative 1. This is also negative 1, I believe. Nope, negative 1/4. And my bad, this is negative 1. There. Okay? So if you take the derivative of this, this is just another way to spell the dynamics we've talked about before. Right, in this case, it is the version that is positive around the origin and then goes down, goes up, where this one is positive 1, negative 1. Okay, so which fixed points are stable in this one? In the deterministic sense? This one is like this. So this one's stable, right? And this one's also stable. Okay, this one's unstable. And that corresponds to the marble going down and landing in this bin versus that bin. That's the same. This is just the potential interpretation of that same dynamical system. Okay, now I'm going to do the same thing. I'm going to make a discrete time approximation and add some random noise. So I'll do maybe with a time step in there. And what I'm going to do now, this is again W drawn N drawn independently from a normal distribution. And what I'm going to do is I'm going to just simulate the particle a bunch of times. And instead of drawing any one trajectory, well, we can do one trajectory too, but I'm going to just draw the histogram. Okay? I actually pulled it up over here. I mean, this is actually the result of simulating a bunch of times from a bunch of initial conditions. This is now time, okay, and this is the x position. So you see a lot of trajectories go down and end up in the vicinity of the two fixed points. And I think it's more visual to see it here. If I start with even, all of my particles right at the 0, and then I hit go, then what happens? I don't stay at 0. Even the unstable fixed point is no longer a fixed point too. I've added noise, okay? So I quickly, I think I can, this is the one where, yeah, right? I quickly diverge from that unstable fixed point, and all my particles tend to roll down the hill, okay? And then they find new distributions around these new wells, okay? So think about this particle rolling downhill, but being constantly subjected to small random noise, like in Brownian motion, famously of little particles moving, jittering around. But it's actually more interesting than that. So that's a beautiful picture where you get these nice distributions peaked around the basins here. But if you look at individual traces of this, right, any one guy is not only just bouncing around, but if you watch it long enough with Gaussian random noise that has infinite support, right? So there's some probability of getting large noise at any time. It might be rare, but it'll eventually happen. And what you also see potentially a series of noise that are all similar could happen. And you'll see these sort of random escape attempts, they're called, okay? Any one particle might actually jump from this fixed point to this fixed point, right? Or jump back. So the trajectory of any one rollout can be very complicated. It would tend to, I would guess it would, from this initial condition, with high probability, it'll go down and hang out here for a while, but there's always some probability that it'll jump over here, okay, and potentially could jump back. Now that's going to have implications for things we're doing going forward. But I think that picture is a beautiful generalization of sort of what we originally saw with these stable fixed points of the deterministic system. Now, what we'll see is that even though one particle is complicated, the distribution can be very simple and can actually converge. Okay, so what is the machinery we'll use to do this? Let me pause that because that's irritating. Okay, so let's just give a little bit of notation. I'm going to use the notation P of n x to be the probability density for xn. So this is some function over x that tells me the probability of being at that particular x and at step n. Okay? So while I still want to write our dynamics mostly using the differential equation or difference equation form, it's important to understand the Markov chain or Markov process form too. There's a fundamental equation that governs the distribution, which if I start with P0 of x, which is my initial conditions, then I can write P of n of x as since I have continuous states here, it's going to be an integral of some conditional distribution n minus 1 of x prime dx. Okay, so there is some dynamics just governed by the simple laws of probability here, which tells me if I have a distribution of possible x's at time n minus 1, I can use an update to come up with the distribution at time n. And in fact, this is the conditional dynamics distribution, which corresponds with, we'll see some examples, this I can go back and forth from my differential equations or difference equation form and this distribution form. This equation of how the densities update has a lot of names. You know, it's called, for instance, the master equation in a lot of fields. There are forms of it that have fancy names that we'll talk about. You might know it as a continuous state Markov process. And it's beautiful and simple. There's an obvious extension of it where you have conditional distributions that are dependent on u, and that'll work too. Okay, so we're not going to sling around too many probabilities today, but I want to think about the dynamics of the distribution now. I'm telling you that I think that the dynamics of the distribution can be simple even when the dynamics of the any individual trajectory are complex. Okay, and there's a great example. This is my favorite example of that that I have to show you. We've talked a lot in this class about nonlinear dynamics, but I've never actually mentioned chaos, even though that's a favorite topic of nonlinear dynamics. Okay, so it's a good example for this. So let me give one of the very simplest example here. Okay, the exact equation isn't super important, but I'll put it up since it's easy. The interpretation, I hope you can work through here graphically. So if I have xn plus 1, this is actually a deterministic dynamical system here. Okay. The curve looks like this. Okay, between 1, 1, and 0, 0. Okay. Let's just think about what the dynamics of the deterministic system is. This one, it doesn't even have noise. It's already crazy. This is one of the simplest examples of chaos. What does chaos mean? Chaos means that if I start with slightly different initial conditions, then I'll have very different trajectories. There's a strong sensitivity of my trajectories to initial conditions. And I can illustrate that with a few steps of our little staircase method here. So if I started from some initial condition, let me just pick this one. The way we do the iterated maps is I figure out what xn plus 1 would be, and then to get from that xn plus 1 to the next one, I do the staircase method, okay? I'm going to walk around, and what you'll see is if I can do this right, this thing's going to bounce all over the frickin' place, okay? Boom. Something like that, okay? So if I were to have changed the initial condition just a little bit, I could have taken potentially a very different path. This is a very simple system that has very interesting, complicated rollouts. Okay, so I spent time writing some of the notes this morning, so I'll put them up. Okay, so this is just two different simulations from very different initial conditions of that logistic map. Okay, so the trajectories look very, very different. Now here's the beautiful thing. If I ask a different question for this system, if I say, let's assume I have an initial density distribution that's just a uniform distribution between 0 and 1. And I propagate now the distribution of states through the logistic map. Okay? Then what happens? In fact, this one is even if the initial conditions are the only source of randomness and the dynamics are random, are deterministic, I can still ask this question of take a probability distribution here, propagate it through this map. Every individual trajectory is complicated, but this is one of the simplest systems, or one of the systems where we can solve for the distribution in closed form. The equations are here in the notes, but I won't put them up. And look what happens. Let me see if I can make that way bigger. It turns out, so I've plotted a uniform distribution between 0 and 1. Okay, the probability density of being in any state x is 1. That's my initial guess. After one iteration of the map, I can say what's the probability of being in any x? It's this blue function here. After two iterations of the map, what's the probability distribution of being in any state? It's this blue one here. And it converges extremely rapidly to a stationary distribution, which is that dashed line that I plotted all the way across. Okay, it turns out that's also true for this system up here, that even with random noise, although any initial trajectory, any particular initial condition simulated out is going to be a complicated path, the dynamics of the distribution, of the probability distribution, are simple and converge fairly rapidly to a stationary distribution. Okay. A stationary distribution is just going to be a fixed point of this master equation, of this Markov process. So that P star of x, or Pn plus 1 of x, equals Pn of x equals P star of x. So this is the first lesson from stochastic systems, is that oftentimes the distributions can be very simple, very elegant. How many people are science fiction fans? Anybody? Yeah? Every time I think about this, I can't help but think about, do you know what it's going to be? I can't help thinking about the foundation series. Yeah, right? It's like the whole premise of the empire, right? Is that it's psychohistory. So the premise of this, I love Isaac Asimov, by the way. But yeah, the whole premise of this very successful series is that it's very hard to predict the future of any individual. But it's actually very easy to predict the population, the dynamics of a population. And that guy there, Harry Seldon, made a prime radiant so you can predict the future and steer the empire. Yeah, I love it. So it's a very, very compelling idea. Sometimes very complicated dynamics can be rendered easy just by putting them into this probability space. Sometimes control can be made easy, not always. Okay. All right, so that's the number one lesson. I also want to think about, when do we need this and when do we not need this before we're done with the lecture. I'll drop a couple more names just for people that are trying to make connections to other things you've heard. So this was an example of random initial conditions. Plus deterministic dynamics. That's enough, right, to talk about probability distributions. You don't have the dynamics need not be stochastic. You can just have random initial conditions. And asking the question of how does a distribution propagate through a deterministic system, that's the stuff of Perron-Frobenius, right, and Liouville theorem, if you've heard these names. So occupation measures. I just want to some of you are using those kind of tools for your project, so let me just make that connection. Okay, it's just a reduced form of the master equation, which the emphasis is on how those densities propagate through deterministic systems. Okay, questions about that? How many people have actually read the Foundation series? Yeah, you should go read it if you haven't. If you didn't raise your hand, go read it. It's great. Except for the part about the mule, that's kind of a weird part. Little long-winded. What's that?
Opinions on the TV series?
I guess I haven't watched. I didn't even know there was a TV series. Sorry. That's pretty new, right? Yeah.
Apple's doing it.
Ah. Is it out yet or is it not out?
First season.
First season, okay. Geez. So like very topical and I totally missed that connection. Do you have opinions about the TV series?
The camera guy?
Yeah, right. Okay, I'll ask after. Okay. That was lesson one. The stochastic dynamics can be simple even if the deterministic or the single path dynamics are complicated. There's another lesson that I really want to land here, which is that there's a nuanced connection between the randomness that you're putting in and the stability of the deterministic system. And you can see that actually very clearly even in just a simple linear Gaussian system. I'll do it even in the scalar case. So let's just think about the simple linear system. It's the one I derived initially, actually, right? And I'll say Wn is just drawn from a Gaussian distribution with zero mean. I'll call it sigma W squared. This is another place where we can think about propagating solving the propagation of this master equation in closed form. Okay. So if I said P0 of x is also a normal distribution. I could give it some initial mean, but let's just keep it as a Gaussian distribution centered at the origin. So I'm going to use this as time step again. So this is, I've got my quadratic potential function. And I've got an initial distribution, which is some Gaussian. And I'd like to ask, how does that Gaussian, which I've got another distribution of noise that's added on every single time step. I'm going to add some noise. And I've got two competing dynamics. I've got noise that's trying to, keep me away from the origin. It's pushing me around. It's adding random stuff to it. And then I've got this stability of coming down from the linear system. I've got potentially stability if A is between 0 and 1, pulling me in. And what you'll see, and what we'll see clearly, is that there's some tension between those two, but they come into perfect harmony, where the stability pushing me in and the noise pushing me out will exactly balance, and this lends itself to the stationary distribution. The beautiful thing about linear Gaussian systems is that if I want to write p of x given x prime for this equation, this is really just going to be another normal distribution, but it's centered at the mean is a of xn, or x prime, I guess. You have to think about that. Okay, so I have, I'm at some particular state. My marble's at some particular state. Okay, what's the dynamics conditioned on being in some particular state? What's my dynamics going to be? The true dynamics is going to move me forward to a x prime, and then there's going to be a Gaussian that adds it to it. So this is equivalent to just having a Gaussian around the place where my deterministic dynamics would have pushed me. If I want to multiply, you take the integral of the convolution of this function with another Gaussian. Gaussians convolve, okay? And I get a solution which, in order for p of n plus 1 of x to be this times the previous one, I get a covariance that's a combination of the noise that's been added and the stability that's been added. This is just, I wrote it out carefully in the notes, but this is just integrating the Gaussians, okay? And you can see, what you see is that there's a dynamics of the variance of the distribution. And in fact, you can see that there's a steady state covariance, where these things come in balance, that is, as you'd expect, a harmony that is, comes between the stability properties. I've got a noise distribution that's pushing me out, and a stability that's pushing me in whenever A is between 0 and 1. That's well defined, whenever that system's stable. I'm trying to decide if I chose the right level of detail. I don't think you want me to write out all the Gaussians, but that might have been too little. So ask questions if you have them. The dynamics of the mean will just march forward in the standard linear dynamics. Okay? But the competing forces of stability pushing in and randomness pushing out. It's a beautiful dynamics. And it comes in all shapes and sizes when you're thinking about much more complicated nonlinear systems. When you're a walking robot that's walking over rough terrain, you're a UAV flying through wind, these are the competing forces. Yes?
Can you say again what sigma n is?
Good. So the probability distribution n is, I'm writing as mu n and sigma n squared. So at 0, I've called sigma 0 to be my initial covariance of my distribution. And I want to ask, how does the variance of that distribution evolve over time? And I say it evolves to a fixed point, which is sigma squared star.
So how do you get the 1 minus a squared in the denominator?
If you have sigma n plus 1 squared is sigma w squared plus a. Did I miss a squared, maybe? I must have missed a squared here, I guess, right?
Yeah, and then it's geometric.
Yeah. Yeah. Thank you. I'll check that, but I think that's right. Yeah. Okay, so linear systems, beautiful things. Either they converge to the origin, to a steady state Gaussian covariance in the case of linear Gaussian, or if A is unstable, then actually it will not converge, right? Of course, all the particles will go off to infinity. Nonlinear systems, of course, can do much more subtle things. The logistic map is one example. Let's do another example, which I think is really almost the same as what we just did, but importantly different. Let me do another cubic. But this one is, I'm going to flip it upside down. So this is the one that looks like this. So this time, now this one is the stable fixed point, and these are unstable. Okay, and I'm going to make the discrete time approximation of it. Okay. Here's my question for you. What is the stationary distribution of this one? Yes?
Won't all the particles leave the stationary point given enough time?
Exactly. There is no stationary distribution for this. Okay? What you'll see if you start off with an initial distribution, let's say even at the origin or whatever, you'll see a lot of particles hang out at the origin, okay? But there's some probability of escaping past this. As these things bounce around, they're going to take escape attempts, right? They'll eventually find their way over here. And if they do, they're off to negative infinity. If they do over here, they're off to positive infinity. As time goes to infinity, actually, your density of particles that's managed to survive at the origin eventually decays to 0. and there is no stationary distribution. Now, to get philosophical, I guess, I actually think this is what happens in almost all of robotics, maybe. So people ask about, how do we prove that autonomous car is not going to crash, right? Eventually, something's going to happen. You're going to crash. How do you prove your walking robot's not going to fall down? If you're making an honest model of the world that you're navigating in, at some point you're going to cross the street and I don't know, a Mack truck is going to come by and it's going to knock you over, and you just can't. If you've modeled the world, you can't prove. So it's very interesting now to think about how do you talk about the long-term stability of a system that's faithful about saying that there is some probability of failing at all times. In fact, this is actually one of the simplest examples. Do you understand what the distribution is going to look like? It's going to look like a Gaussian for a small amount of time, and that Gaussian is going to be like a balloon with a small leak, and it's going to, until it's got zero mass here. That's what the distribution will look like if I plotted the histogram. So there's a name for things like this. This is a metastable. Oops. Fixed point. It's a metastable system. People talk about metastability. A lot of people think about diamonds. There's some probability that a diamond will turn to coal, I guess, right? And but it's still pretty valuable. It still takes a long time for that to happen, and we still invest a lot of money in diamonds, and still, like a walking robot that hangs out here for longer than the one that falls down all the time, somehow we should be able to quantify that in some interesting way. So there is a branch of all of these analysis that talks about quantifies the metastability of the system. That there's these long-living transients that aren't stable in the classical sense, but they have the rate at which that unstable system fails is of interest. And you can talk about optimizing the metastability of a system. Okay, here's another one that I like a lot. Okay, this is the van der Pol oscillator, but with noise added. Okay, so just the same van der Pol equations. It's going to go on that black nominal limit cycle, but I'm going to add noise, small Gaussian random noise on every step. What's the stationary distribution of this process? Does it have a stationary distribution? Yeah.
I don't know if this is how it would work out, but if the points could eventually hit 0, 0, they could get stuck there. But I guess you could also say that that's an infinitesimally small probability.
If I'm doing additive noise, though, then even if I started at 0, I would in one step leave 0. So, and the dynamics, as you remember, will then try to push it towards, right? There's a competition between two forces, right? Good and evil, I don't know, stability and chaos, right? So we've got noise pushing me out, stability pushing me towards the limit cycle. What's the stationary distribution? Yeah?
It's going to be like a band around there.
Why is it going to be a band around there?
We will try to deviate a little bit, but then it will push back.
Right, so the intuition is that he says it'll be a band around the limit cycle. And the reason is that that's the correct answer. We'll see it in a second here, that the stability of this cycle is that you have a stability back to the manifold, but there's no stability along the cycle. Okay, so if the particle walks along the cycle, if the random noise pushes it along the cycle, it will not restore itself in that direction. In fact, I spent a little too long making this animation. Goes like this, yeah? Kind of bunches up. It's kind of fun to watch. It's like alive. Okay? But that's how this Gaussian evolves. Right? right? It gets slowly and slowly stretched out. And then rather than make a video that consumed hundreds of megabytes, I just took a frame at the end of the, at time 1000, it's all stretched out like this. Okay, so nonlinear dynamics and probabilities are just this beautiful thing. Now, I can't give you a closed form solution. I can't even give you a closed form solution for the limit cycle, the nominal limit cycle. That's a numerical solution. And I certainly can't give you a distribution of the, along that cycle. It's not some simple Gaussian centered around there, right? You can see it's bunched up in corners and stuff like that, right? Actually, I guess it's more bunched up in that corner and spread out in that corner. But these things are real quantities that we need to use our control tools to reason about. Okay, so quick aside. So since some of you are using this for your projects and everything, there's a strong philosophy, I guess. I tried to be very careful in Drake about, how we model stochasticity. Again, systems are f of x, u, but potentially w, okay? And we can have outputs y, inputs u, for instance. When you write a system in Drake, certainly all the systems that are in Drake proper, that system is never allowed to be to call a random number generator. Not allowed. You've broken a rule. If you want to have a stochastic system, you must add an additional port, W, and you can add a random port, W, okay? And then there's some tools to make it automatically introduce a random variable input. Now, there's a couple of reasons for that. First of all, if you start adding randomness in here yourself, then you will defeat the smarter integration routines. So for instance, if you wanted to have a Gaussian white noise process and we started doing variable step integration for accuracy, you have to do that carefully. And so we've done that carefully a few times in this sort of random noise block. And then it'll be right every time you do it. But it's actually way better than that. It's way more important than that, right? So by taking that decision, it's very easy to get repeatable simulations. If I want to set the random number generator that defines this, even if I'm simulating a random, huge complicated diagram, if I just lock in the random seed, then I get a deterministic play, I can play the same random thing twice. So there's choices around that, and you can play the deterministic thing if you want. Moreover, when we do the control design, this is the standard picture you'll see in robust and stochastic control. And the control design philosophy, I can ask any system or any diagram to, for instance, take gradients with respect to its randomness and get a sense for the covariance matrix, right? And I can write explicit verification, control design, system identification tools, all in this beautiful sort of framework, as long as I know which ports you're calling random, because I'll treat them a little bit differently. Okay, so there's there's plenty of tools for doing stuff with random processes in Drake, but there is a strong philosophy that please don't call rand in your generator. Yeah.
You mentioned as long as you know which ports are random, I'm assuming that's system dynamics plus some random offset. Yes, it's not, you don't need your randomness entirely input separately. So when we declare input port, you can say declare a random input port. You can say declare input port, this one's random. And you can even tell it what type of randomness it does, so it knows it'll hook it up yourself up for you. But then we are asking, I think it's the thing you said, surely you're not doing this. I think I am doing that. So I am asking you to then take that Gaussian number, or whatever rand call, and write just inside here just the nonlinear function that warps that into whatever form you want. I see. So we're taking a random input, and then we're deciding how to add that into our variable.
Correct. If it's additive, it's very simple, but it can be much more rich than that. And even additive, once you
have a dynamic system, it can get very rich very fast, as we've seen. Okay, let me work through, I think, another example that's now connecting this back to walking. So it's one of my favorite examples of how these, how the stochastic processes touch our interesting dynamic robots. It's a simple example because I haven't told you anything about stochastic control yet. We're just talking about stochastic dynamics. And we'll do stochastic control examples on Thursday. So let's think about what it would be like to think about the rimless wheel on rough terrain. Okay. I think I have a video here. Yeah, here we go. Okay, so rimless wheel, that's a pixelated old video, I guess. But, okay, you can sort of imagine what it might do. It wants to roll. It's got a rolling fixed point when the terrain was fixed. But if you now say on every step, the terrain is drawn from some distribution, then we get a different dynamics. This thing will roll for a long time, but there's some, actually that's the one where it stops. Okay, so there's always some probability of it having too big of a ramp, and it'll run out of steam and stop. We have the nominal, terrain be the one that has a nice stable fixed point, but we're going to draw it from random. So let's just think about how that plays out. So let's remember that we have, for the deterministic rimless wheel, we could compute the Poincare map. This time, when I did it before, and my favorite version of it for the deterministic thing, I put the coordinate system, the return map, starting when the foot's on the ground and ending after the next impact when the foot's on the ground. That's the simplest math, I guess, and the cleanest presentation of it. But it doesn't work if your ground's going like this. That's like a moving coordinate system. So no big deal. We'll just take a different slice, a different Poincare map. We'll do it at the apex. So it's when the stance leg is vertical until the next time the stance leg is vertical. Okay? It's going to make the picture look slightly different, but the ideas are the same. So this is the apex to apex map. So at the apex, theta is fixed. The variable of interest is theta dot. The velocity of the leg at the apex, the velocity of the leg at the next apex. For these discrete systems, I'm going to draw the line of slope 1 that tries to go through the origin. And we know that the original system had a stable rolling fixed point, and indeed the deterministic return map looks something like this. With a stable rolling fixed point here. Now it's interesting to think about how to add, we talked about this randomness that comes in once per time. The rimless wheel, I want it to be just walking on rough terrain. So you might think, okay, I'll call a random number generator at the beginning, I'll make some random terrain, and I'll just think about how we evolve on that random terrain. The way we're going to make it fit into the framework is that we'll say that the return map is such that each time I visit the apex, it's as if as soon as I visit the apex, somebody draws a random number of the terrain below me. Okay, so the stochastic version I'm going to choose the ramp angle this angle here was theta, this angle here is gamma. Choose gamma at each footstep such that it's drawn from some random distribution. Okay, so it's as if someone is just like laying the track down in front of the train, right? As the rimless wheel comes up, someone puts down a thing, it's going to be at the nominal ramp plus or minus some Gaussian number. Takes a step, gets to the apex, draw another random number. And I've just plotted it like this to make it look normal. Okay? Now what does that do to the return map? Right now, our return map is stochastic. It's a stochastic process. So you can plot it in various interesting ways. But if you think of it as being, I have my nominal return map for any given theta dot, since there's some draw, there's some distribution of possible outcomes of the next theta dot. Okay? For any given thing, I've got a distribution that looks something like this, right? It's not exactly a Gaussian, it's a Gaussian shoved through the rimless wheel mechanics. Were you raising your hand? No? Okay, so we have a stochastic apex to apex map, which fits right into our stochastic discrete time systems. But it's beautiful in the sense that the return maps abstract time away. So we've made this time-like variable that's representing the geometry of the map. Okay. All right. So what is the stationary distribution? What do you think? Every time somebody draws the ramp, what am I going to come into the rolling fixed point? Maybe bounce around the rolling fixed point. What's the dynamics of this distribution going to look like? Eventually, someone's going to draw a piece of terrain or a couple small, flat enough terrains that I'll come to rest. The hope is that I have a long-living time transient where the stability converges around this fixed point in the deterministic system. But like my very simple example, it will slowly leak probability, like that balloon. It's going to slowly lose its probability and end up standing still. If I watch that system roll out, if I were to run a bunch of them in parallel, like people do in their robotics paper videos now, right? They just have like more and more of the rimless wheels would come to rest. Some of them would keep going for a very long time. Actually, it's very interesting to compute the mean first passage time. That's a meaningful metric here, is like, what's the mean time to failure of the rimless wheel? Okay, and they can be really big numbers, depending on your distribution of your terrain. All of those things you can sort of compute, and those are the meaningful statistics of these processes. But eventually, it will fail. So here's the dynamics of that probability density plotted on the return map. Okay, you start it from some random fixed initial condition, you run it, and it will converge rapidly to the neighborhood of, it's slightly skewed, it's not Gaussian anymore, but it's converging to the neighborhood of that rolling fixed point. But if you let that run long enough, it'll slowly run out of steam. Okay, here's the staircase deterministically. Here's now small, rough terrain. This is Katie Bill. She did some awesome MATLAB animations. Watch this. Whoa, right? That's
the almost stationary distribution, the metastable distribution. And it has all the statistics. We have ways to compute that metastable distribution and talk about its time constant and the mean time to failure. That was the work in her thesis. Okay, so, a couple main ideas. We said that the probability distribution can be simple even if the dynamics are complicated. We said that there's a trade-off between stability. There's a force, stability pulling you in, noise pushing you out. That's a standard dynamics. And this whole notion of, metastable, or the things of stationary distributions, and the fact that things will actually often leak probability, and the quantity of interest might not actually be the stationary distribution, but some prior transient distribution that's hopefully long-living. But I want to just ask the question. So I can't help but think of this, like we talked the whole semester and we didn't really talk about probability until now. So do we need this stuff always? Did we just invalidate everything we've talked about? And I think there's an important point to make here. And so let's just compare two different types of disturbances. Okay, so this is I would consider a rare disturbance, right? So every once in a while, some jerk comes and kicks you in the midsection, and you have to reason about that. Okay. We've been doing pretty well with our tools from deterministic feedback control and analysis for that kind of disturbance. That kind of disturbance looks like, in my mind, an instantaneous change in the initial conditions. If you're stable with respect to a lot of initial conditions, then when someone comes and kicks you, you think about that as a change in initial conditions, and you hope to be stable. Once you've received that impulsive kick, right, then your dynamics are deterministic, and the convergence of your deterministic analysis is correct. This is a very different type, like the rimless wheel, for instance, or if you're walking now on rough terrain, like we just did, that's a very different question, because saying that you're stable in the deterministic sense is no longer relevant. If the rate at which your noise affects you couples with the rate at which your dynamics converge, then you must take them into account simultaneously. I'm saying this only in a very philosophical way, I'm sorry, but I think that could be made precise, right? So there is some time constant of stability. There's some time constant of the noise affecting you. If those things are very separated, if the noise is very random and your time constant, your stability is strong, then you deserve to think about it as a deterministic system in rare events. When those things intermingle and the noise impacts your stability, then you must put them together. Okay, so those are two different sides of the spectrum. Now we're seeing a lot of, I think part of the excitement in RL, for instance, is that people are using randomness a lot and getting robustness out. So there are possibly, we'll talk about it again a little bit on Thursday, there are some ways where adding noise could actually make your control problem easier, could make being robust to noise could be a good way to be robust to different types of uncertainty. We're still learning those lessons. But I think that first question of whether you must analyze it is made by this example. Okay, I'll just make one more point here, which is that, and we'll really talk about it on Thursday. But the modeling that you do for your plant, whether it's a stochastic model or a deterministic model, can change the way you do your control design. Right? So this is just a compass gate now walking over rough terrain, but you notice that the terrain is on average flat. Okay? This is a controlled compass gate. If you design sort of the optimal, this is a small enough system we could do brute force dynamic programming. You ask for the optimal deterministic gate, controller for this compass gate, and you then apply it to stochastic rough terrain, it does very badly. If you ask for it to, for instance, have the largest mean time to failure possible, and you give it the dynamics of the stochastic terrain to chew on, then you can have a much
stronger control design. So those modeling decisions will impact the way you do control, and that's the goal for Thursday. There's a bunch of other pieces that before we get to control, there's a bunch of other spin-offs from this, right? So if you might think about uncertainty quantification. This is a whole branch of work that some of you might. I can't remember if anybody's working on that in this in the class this term, but there's great fields. I think it ties in closely with the field of verification, right? And certainly just all the stochastic analysis I think is very relevant for robotics. Good, and we'll do robust control on Thursday.